Harry who gave a talk here over a month ago. We will talk about lower bound expansions for random Bernoulli matrices via novel integer partitions, so combinatorics and probability. If you like the talk, you are welcome to join us for dinner at 6:45. It's the usual place. But you have to let me know immediately after the talk. Thank you.
Okay, thank you. It's a pleasure to be here. And today I'd like to talk about some work I did on random Bernoulli matrices. And so I'll define what a novel integer partition is very soon. First, I want to go through what is a random Bernoulli matrix and some known results, and then go on to the definition of what I mean when I say a novel integer partition, and then some future directions at the end. So first, a random Bernoulli matrix is an n by n matrix in which all entries are +1 or -1 with equal probability, independent of all entries. So it's the very simple object to state. Each entry, you flip a fair coin. You give it a plus or minus 1. And the fundamental question that we're going to be thinking about is, what is the probability that such a random matrix is singular? And this is one of those great problems that is very simple to state, very simple to sort of start to think about, and then it gets very complicated very quickly. And so, for example, it's not even known whether or not the probability that a random Bernoulli matrix is singular. It's not even known whether or not this is a true statement. So what is this probability? So this is asking, well, what is the probability that any two given rows or any two given columns are linearly dependent? In other words, one row and one column line up either exactly or one's the opposite of the other. Okay, so this 1/2 to the power of n means you go 1 by 1 by 1, you flip the fair coin, it's got to be aligned. This second term here, n choose 2, means you take any n choose 2, any pair of rows, any pair of columns. That's what that one factor of 2 is, and then the plus or minus gives you the other factor of 2. So I don't actually know.
This is open?
This is still open, yeah.
Wow.
And I actually don't know
and
who
all
the
the smart people tell it now who did matrices could not prove it?
I will tell you what he did. Yeah, he did some very good stuff. Yeah, they all did some very good work, but it's a notoriously difficult problem. Yeah, it's deceptively simple to state, and then yeah, it just gets really complicated. Yep.
But for small n, you can compute it exactly.
Exactly. Yeah. So up until maybe like n equals 10, right? Because then you got a 2 to the 100, different possibilities. So, then that's where you maybe do some random sampling, and then you can kind of get a better picture. So. And I actually don't know who to attribute the conjecture to. Some papers say it's Erdős, some people say it's folklore or something. So it's a very, long-standing open problem, and some very, very important people worked on it, like Komlos, who got the first, as far as I can tell, the first result which says that the probability even tends to 0. Okay, so it wasn't really even known. It was even conjectured that maybe the probability didn't even go to 0. At one point. There is some computational evidence when you look at n equals 2, 3, 4, 5, 6, it kind of like goes up at first before it then goes, crashing down. So maybe, 50 years ago when they could only look at n equals 6, it was kind of that indication. So Komlos was the first to show that it tended to 0. And then you may have heard of some of these gentlemen here. They were the first to show that it decays exponentially. And the bound they proved was 0.999 to the power of n. This was later improved by Terence Tao and Van Vu in 2007. And so the bound they proved was that it was at most 3/4. So this is 1/2 is the goal, and they got up to 3/4 using their techniques. And then a little more recently, Bourgain, Vu, and Wood came up with, they squeaked out a little bit more efficiency out of the same method, and they got 1 over square root of 2 plus a little of 1.
You mean Philip Matchett Wood or Melanie Wood?
Philip Matchett Wood. Okay. And in fact, so the motivation...
You guys PhD here.
Exactly. Oh, okay, yeah, exactly. So the motivation actually came from when Philip Matchett Wood gave a talk at USC, and we were in the audience, and we said, oh, okay, what can we say about this problem? So that, as far as I can tell, and I've asked around, this is still the best upper bound that is known.
And the true one is 1/2.
Well, the true, it should be 1/2. It should be. But it's, as you'll see, it's really complicated, and It's much more, there's a rich substructure going on which kind of indicates why it's not quite so easy to prove.
So 0.99, then 0.75, then 0.707?
Yes,
and
exactly.
now you need 0.5.
Yeah, now we need 0.5. Exactly. Well, that would be nice. Yeah, you might turn a few heads if you can get that one. And of course, one of the motivations was we listened to this great talk by Philip Matchett Wood, and then we read the Kahn, Komlos, Szemeredi paper. And in it says, of course, the guess may be sharpened, for example, 2, and you take away the first term, and you might ask, well, let's suppose the long-standing conjecture gets solved. What would you do afterwards? The day after, what would you do? And you might prove an asymptotic expansion, for example. What's the second order term, third order term, etc. And it lists this term here with no justification other than to say, the right-hand side being essentially the probability of having a minimal row or column dependency of length 4. So basically 4 linearly dependent row vectors or column vectors. And again, you have 3/8 is the exponential factor, and then you have this n choose 4, choose any 4, and then some factor of 2 for pluses and minuses. So taking this a step further, what we did was we said, okay, well, what is the structure here? So when we think of a null vector of the form vi plus or minus vj, we think of this coming from a template, a coefficient template of 1, 1. The coefficients here and here are 1 and 1. Forget about the plus and minus, forget about row and column. There are 2 vectors that are causing this singularity. And then you can take it a step further and say, okay, when you have null vectors of the form, there's 4 of them, that corresponds to template 1, 1, 1, 1. So we're just extracting the coefficients. Order doesn't matter, pluses and minuses don't matter. And then more generally, you could look at null vectors of the form, lambda 1 to lambda k, and that we would say corresponds to template lambda.
What do you mean by null vector? So annihilating the matrix?
Sorry.
What do you mean by null vector?
But a null vector basically just means you multiply this by the matrix, you throw in zeros appropriately, and then you get the you multiply it and you get the zero. So that by null vector, I mean you pad it with zeros as appropriate, basically. Yeah. Another motivation is from a paper by Oglisco in 1988, and he looked at rectangular sized matrices. So these are not square matrices, but he looked at a slightly different problem. You might think of it as like a pre-singular matrix. So it's like you look at collections of plus minus 1 vectors, and if you just added in one more row that's just the right combination of pluses and minus 1s, you would get a linear dependent set. Okay, so it's kind of like a pre-singular collection. And it's really about, the question they were looking at came from, I think, psychology results where they wanted to know about associative memories and how you can sort of, take collections of memories and say, oh, well, you can kind of get another memory out of it, something like that. And so there you do get, an asymptotic result. You get, p is asymptotic to basically 3/4 to the n. This is where the 3/8, this is kind of like the pre-singular, the 3/8 turns into a 3/4. You have one less degree of randomness. So combining these two ideas, what you do is you look at the event that there is some right or left null vector of the form lambda 1, lambda k times the appropriately padded, vector, and you define d lambda as the event that the singularity was caused by that form of a null vector. And so the conjecture really is that P of S is asymptotic to P of D11. In other words, what you're really saying is that the real thing driving the singularity is this 1-1 type of null vector. And what we're saying is, well, what would the runners-up be? What would happen if you say, well, excluding the most likely way, what would come next? And so the answer that we sort of, well, not the answer, but we conjecture, what we came up with was that it ought to be, the next one should be 1, 1, 1, 1. The next one after that should be 6 1s. And the next one after that is 8 1s. The next one after that is going to be 2 with a 1 with 4 1s. The next one after that is going to be 10 1s, then a 2 followed by 6 1s, etc. So it's not just a bunch of 1s. There's this really intricate structure going on. And there are certain questions you might ask yourself like, what partitions are part of this expansion? Why did we leave out certain ones? How come there aren't any of size 3, for example?
You can continue it indefinitely?
You could potentially continue it indefinitely.
It gets harder.
It gets harder. Yeah. So I hope I can convey what we've done and why what we've done is a good starting point, and maybe it might entice you to think a little bit more critically about it and see what you can come up with. So there is an actual theorem in this paper, and the theorem is that this is a guaranteed lower bound, which is, it's basically saying, all right, this is definitely at least what's going on. Now, this statement, this theorem, the way it's stated, could potentially also be the first 8 terms of the asymptotic series when the conjecture is resolved and the stronger versions are resolved. Okay. And if you look here, the structure is of the form, 1/2 to the n, then 3/8 to the n, then 5/16, so that's the 6 ones, and then 35 over 128, that's 8 ones. And then something interesting happens at the 5th term, and this is where you got to start thinking a little bit more creatively. We're not just summing over all possible null vectors, we also have to think about combinations. You could have a 1-1 on one side, and you could have a 1-1 on another side as well. So there are interactions between multiple occurring events. So you could have 2 1-1s occurring at the same time, and that's what this term here says. It says, okay, there's a contribution of the form 1/4 to the n based on a linear combination of 5 vectors, which have this 2 and 4-1 structure. But then there's also this contribution from interactions between these null vectors as well. Okay, so it gets a little more complicated. This could very well be an actual asymptotic expansion to this number of terms. If you were to keep going, you'd have to look at interactions between all possible pairs of all possible null vectors.
Are these numbers that show up, are they just like the expected number of those violations?
Exactly. So these are really just the first moment expected number, and then this term here is basically the second moment. Exactly. So this term here, second moment, is very similar. The calculation, the work is very similar to a lot of the calculations in this Poisson approximation regime, where you look at the first moment and then the second moment, and you have to look at all possible cross products between 2 elements. So it's a very similar calculation. But if you keep going, if you all go all the way down to, say, 1/8, you'd have to look at 3-way coincidences between these 1-1. So like 2 here, maybe 2 coming from the column. So you have to look at all possible interactions. But at this high level, at this first stage, right, if you interact between 1/2 and 3/8, you get 3/16, right? Yeah, 3/16, that's less than this 7/32, so you don't have to think about those interactions just yet. Okay, so yeah, it is first moments first, but then you do have to consider all possible interactions afterwards. It'll probably make a little more sense as well as I show you more of the structure. Okay, so before I get too much more into it, what is an integer partition? In case you don't know, an integer partition is just an unordered collection of positive integers, typically written in descending order. Now, if you love integer partitions, like I do, you probably think about them differently than how you should probably think about them in this talk. Usually you associate integer partitions with, like, you fix a weight. The sum of all these positive integers is 10, and you look at all of those. Here we're focusing mainly on the number of parts. And so, for example, in this asymptotic expansion, or this guaranteed lower bound expansion, we looked at integer partitions of the form 1-1, 4-1, 6-1, 8-1s, a 2 followed by 4-1s, etc. These are the first few what we call novel integer partitions. And in particular, we're excluding many partitions like 2-2. Why? Just, quickly, it's a multiple of 1-1. If you think in terms of null vectors, any multiple of the null vector doesn't tell you anything else because you're equaling 0, so you just normalize that away. But we're also excluding partitions like 3-2-1. But you could have a combination of vectors that have 3 times this, 2 times that, 1 times that, and you get a null vector. But we're excluding things like 1-1-1 because that's not fairly divisible. You can't, you think about this as a random walk with step sizes, with these numbers, you can't get back to the origin after 3 steps using steps of size 1. And then finally, things like 9-2-1. You go up 9 steps, you can only go in steps of 1, so 9 up, you can only go 2 down, 1 down. So there are certain natural integer partitions that are excluded from this list. And then we say singularity occurs due to integer partition lambda if there exists rows or columns and a combination of plus minuses such that you have some combination that gives you a null vector.
Is a notion of novel partition a novel concept?
As far as I can tell, yes. And it is a new sequence as well, and an OAIS that I...
Otherwise, he's going to apologize. He would have come here, but he had to give a talk in Philadelphia.
Oh, okay. Yeah, so, okay, well, yeah, I'll show you the sequence I just submitted to OAIS that I checked, and I couldn't find anything even remotely similar to it.
It's already there or not yet?
It's in draft form right now. I checked. This paper came out a little while ago, and I guess I just never got around to submitting it, but I just did it now. Okay, so in order to understand why we include and exclude certain partitions, we got to have a couple more definitions and kind of wrap our head around what's happening here. So what you're going to think about mainly is just a random walk with step sizes given by these values here. Okay, so just think of a guy walking, a random walk, a one-dimensional random walk, with step sizes, say, -1, 1. And you want to get back to the origin each time. So for example, if you take steps of size 1 and 1, the way you get back is you go up 1 and then down 1. Or you go down 1 and then up 1. If your step sizes are -1 and 1, you go, right, like up 1, plus 1 goes minus, and you go plus 1, you get plus plus. Okay? So you're really just thinking about this as a random walk who's taking steps in increments of these values here. You list out all possible ways for this to occur. And already you should see some similar sort of structures occurring. And in particular, in general, I don't need to consider integer partitions. I can take any rearrangement of the integers and any combination of pluses and minuses. So we call this the Bernoulli orthogonal complement. So it's basically just all the ways a random walker taking those step sizes can start at 0 and then back at 0. So, it gets a little more complicated. 4 ones, these are all the different ways you could start going +1, minus, minus. So up, down, down, plus, down, up, down, up. And then you take the reverse. And the same thing here. You just take a step in the -1 direction. You just reverse the entries in this column. Okay, so I want to make sure this definition is crystal clear before we keep going. And the other thing to keep in mind is, it's not about the length of the partition. Right? Here's a very much longer than typical partition. It's fairly divisible. If you take a random walk using these step sizes, you can get back to 0. But wherever the 8 goes, everything else has to counteract it. So just because there's a lot of steps in this walk doesn't mean there's a lot of degrees of freedom with which to choose whether to go up or down. And then of course, if your walk is not fairly divisible, you can't get back to the origin. Okay, so for a given partition lambda with k parts, we're going to let v sub lambda denote the set of all vectors formed by reordering parts of lambda. So if I take the partition 2, 1, 1, I'm looking at all basically integer compositions, so all rearrangements of those, the 2, the 1, and the 1. And then I get to throw in all possible combinations of pluses and minuses, and without loss of generality, just make the first one be a plus. Okay, you can choose that. Just make it be plus. But then you get to consider all combinations of pluses and minuses. So with 1, 1, 2, or 2, 1, 1, or 2 plus 1 minus 1, just think about all those possible combinations. Then we define the notion of equivalence. Okay, so this is essential. This is why we're excluding certain partitions. We consider two partitions to be equivalent if they have the same number of parts, and there exists a reordering or some combination of plus minus 1s that make basically the set of all random walks with those step sizes the same set. Okay? In other words, what we're saying is, you might try to have this interesting walk structure, but if the walk structures are essentially the same due to reordering and pluses and minuses, we're going to consider them the same. And of course, you probably want to see an example here. Okay, so for example, you take any scalar multiple, 1, 1, 2, 2, 3, 3, those all have the same plus-minus structure. But something maybe a little more surprising is, okay, we'll take 3, 2, 1. But here, you know, start thinking about this as this is a random walk with step sizes of 3, 2, and 1. Wherever the 3 goes, the 2 and the 1 have to counteract it. That's the exact same structure as the 2, 1, 1. Wherever the 2 goes, both 1s have to counteract it. So in this case, we would say that these two partitions are equivalent, even though they're not multiples of each other. And at some point you might say, do you really need to rearrange them? Can you just look at the partitions themselves? And the answer is no. And this was a good exercise. I had to cook up an example at one point because we asked ourselves the same question, which is, do we really need rearrangements? And so I cooked up this example where I said, okay, these guys do not have the exact same random walk structure, but if you reorder the parts in just the right way, you do. So they would be considered equivalent, even though, you know, you would have to do some rearranging. There's a further notion of, okay, you can have two partitions which are equivalent, okay, and they would have to then therefore have the same size. But you can also have a notion of strict reduction, one that's not, you know, reversible. And so we would say that if lambda and mu are two partitions where mu has at least as many parts as lambda, then we would say that mu implies lambda if and only if the set of all possible walks is contained in the other one. Okay, so in other words, anything that, basically the idea is any singularity that this template, this partition could have detected, this other one would have detected as well, and then some. Okay, that's the idea. There's also a further idea, which is if you can even project away some of the columns. And if you project away the columns and you still get the same inclusion, then you get this kind of even stronger notion of strict implication. Because what you're saying is, aha, not only is it that this is containing all possible ways, but it's like you can actually get rid of certain extra information and imply something that's strictly smaller. I'm about to give examples of all of these, so don't worry. So in particular, the definition is that we define strict reduction if mu implies lambda, but not the other way around. So here's an example. 3, 3, 2, 2, 1, 1 strictly reduces to 2, 2, 1, 1, 1, 1, 1. Everything in here, every row in here, is a row in here. The guys in red are extra. They're not contained in this, but everything in here is contained in this. So if you wanted to detect a singularity, this 2, 2, 1, 1, 1, 1 would detect everything that this the first guy does, and then some. So you might say that 3, 3, 2, 2, 1, 1 is not really necessary to detect singularity. But more importantly now is this notion of strict reduction. Okay? It's not just about this is equivalent to this or this is a subset, but now we get to say, well, wait a minute. This 2, 1, 1 is saying wherever the 2 goes, the 1 has to counteract it. But that's the same essential idea behind the 1, 1. Wherever the 1 goes, the second one has to counteract it. And wherever the 2 goes, the 1 has to counteract it. So when you project and look at just the first 2 columns, you get inclusion in this 1, 1 template, okay? In this Bernoulli orthogonal complement. Okay, so that's why we need that definition of projection. You get to ignore certain columns, and then if you're contained in another Bernoulli orthogonal complement, then you are strictly included. And now I get to the actual definition of what is a novel integer partition. So it's an integer partition lambda is novel if and only if there does not exist any other partition lambda prime for which lambda strictly reduces to lambda prime. Okay, so lambda doesn't reduce to anything else. And among all partitions equivalent to lambda, lambda comes lexicographically first. So that gets rid of all possible, multiples as well.
So there's no quick way to decide whether a long partition is novel or not.
There is a very nice, quick way to decide if a very long partition is novel or not. It's coming up.
But not straight from the definition.
But it's not apparent right from the definition. So this is where this is the route we went down ontologically. And then at some point we discovered this really nice simplification, and that is driving the results that are about to come. Yeah. So I'm trying to set you up with, oh, it's really complicated, I'm not sure I got it quite, and then I'm going to give you the nice simple way to determine whether or not your given partition is novel or not. So here's something that's kind of important. You might want to know this, right? I've defined this collection of objects, and you might want to know, well, first of all, does this set of novel integer partitions, first of all, does it detect all possible singularities? The answer is yes. And is there redundancy? And the answer is no. So it really is the set of indices for which you would want to base your asymptotic expansion off of. Okay? And there's sort of a decomposition theorem which basically says every integer partition lambda is either novel or a multiple of a novel. Let's skip down to 3, is not fairly divisible. So that's easy to determine as well. In other words, you can't get back to the origin. Or 2. 2 is the only non-trivial part of this, which is it implies a novel partition of strictly smaller length. So you can't have a novel partition and say, if it's not novel, you get to go to a smaller, it implies a smaller novel integer partition. That's really nice because that tells you it kind of goes up and eventually it stops. There are some little caveats here, really details that are important, which is, I just told you that the set of novel partitions is necessary and sufficient for detecting all singularities. And now if you're really paying attention, you might say, wait a minute, take n equals 4. I could take, 1, 1, 1, 1, and I could stick each of these in it. Each column could be a row of this, and then no matter how I make a 4 by 4 matrix that is singular due to this 1, 1, 1, 1, it's going to imply a 1, 1 on the other side. So you might say, well, in this case, this 4 1s is not really necessary to describe singularities. But that's why we say acting as left null vectors. Okay, so there's a subtlety where you might say, well, in this fringe case, in this boundary case, it's not entirely, but that's not an issue. Okay, so you want to think of these again as acting as possible left null vectors. Just think of one-sided. That's where you get the nice property. Here is the beginning of the nice characterization of these novel partitions. So we're going to define this A matrix. And it's very simple. All we're going to do is get rid of the redundant information. So you have all the plus minus 1 combinations. The second half of it, which is the minus, starting with a minus sign, just get rid of those. Okay? And then interpret each entry, each of those rows, as just a column of a matrix and call that matrix the A matrix. Okay? So really these are, this is plus 1, minus 1, and I'm just writing plus and minus. And you might notice, okay, A11 is plus minus, A with 4 1s is, here's our plus, plus, minus, minus, etc. And you might notice something, maybe some structure about here. A to a 2, 1, 1, you get back exactly this A11. And this is now what allows you to very quickly determine whether or not your favorite integer partition is novel. You look at the A matrix, and you just check. If it has rank k minus 1, you're novel. If and only if. Okay? So it has to have rank k minus 1, otherwise, and GCD, of course, get rid of multiples. So as long as it has rank k minus 1, then you're good. You just have to enumerate all possible paths that this random walker can take.
But can you construct a superscript lambda fast for very long partition?
Can you construct it fast for very long partitions? Let's see. I mean, I've done it. I may have waited a while, but I haven't really done it more than like length 20. But it does, it can. As you can,
for length, if for length a million, it'll take a while.
It might take a while. Yeah, for length, yeah. It would definitely. I never tried a length a million actually, but that's a good point. Yeah. Now, it's great that you can determine whether or not a partition is novel or not. But then at some point, when you're thinking about the asymptotic expansion, you might want to say, well, is this novel, or is this partition a strong player in the asymptotic expansion? Where does it fit in terms of significance? And this is where we sort of took Littlewood, Alford, Erdős bound, and we sort of did a nice little special case of it. And we were able to show that, let's suppose you have an integer partition, but it's not the sequence of all ones. Okay? So just, it has to be at least two parts which are unequal. Then, the number of columns of